Assalamualaikum warahmatullahi wabarakatuh. Welcome to Wisdom International School's digital classroom for mathematics. So children, we are going to continue this chapter circles. So this is the second session in circles. So earlier in session 1 we learnt about like what the tangents are, how to and we even learnt one theorem which said that the radius and the tangent when they meet at a common point, they always meet perpendicularly, right? So that was the theorem we learnt in the previous session. I hope you people have completed the exercise 4.1. So now we will continue with the chapter. Okay, so number of tangents drawn from a point on a circle. So look at this, we are going to learn how many number of tangents could be drawn from a point on a circle. Okay, so if the point was inside over here, all right, so if the point was somewhere over here inside the circle, you can see that we can't draw any tangent at all, isn't it? See, the tangent is a line which touches the circle at one point on the circle. Okay, the point should lie on the circle. But then look at this, if the point was inside and you are trying to draw a tangent from this particular point, you can't draw it, right? Because if you draw it, it will never be a line which will be outside the circle. See, the tangent is something like this, right? So this is what is the tangent. Now from this point inside the circle, you can't possibly draw a tangent, right? So therefore we say there is no tangent to a circle passing through a point lying inside the circle. So no tangent from the point lying inside the circle. Okay, this is the main point. Now the second thing, what if you had a point over here? See, there's one and only one tangent to a circle passing through a point lying on the circle. So earlier we saw that if the point was inside the circle, there were no tangents drawn. We can't draw a tangent. If the point was lying on the circle, we can draw one and only one tangent. Okay, and this is the tangent. This is the tangent which we can draw passing through a point on the circle. Okay, so one point, one tangent lying on the circle. Okay, point lying on the circle. Now coming to the third thing, what if you had a point outside the circle, somewhere far away from the circle? So from this point you can actually draw two tangents. Okay, so one touching over here, the other one touching over here, not more than two. Okay, so there are exactly two tangents to a circle through a point lying outside the circle. So these are the three things you need to remember. So circle, when I say circle and when I talk about a point, there could be only three kinds of point. One is inside the circle, the second case is on the circle, the third case is outside the circle. So how many tangents can you draw when a point lies inside a circle? You will say 0. If a point lies on the circle, only one tangent can be drawn. If a point lies outside the circle, two tangents can be drawn. That's it. There is no other case, right? So only these three cases are there. That's all. Okay. So now we'll come to this. Okay. The length of the segment of the tangent from the external point P and the point of contact with the circle is called as the length of the tangent from the point P to the circle. So what they're saying is, if you have a circle and if you have a point over here, then this particular point and this particular, see, this is the tangent. Okay, this is the point of contact of the tangent. So this PQ, this is what is called as the length of the tangent. That's all. Okay, so they'll give you some measure for this. You know, you will have numerical problems related to this. So they'll give you some length of the tangent measure as something like 4 centimeter, 5 centimeter, and they'll ask you to solve problems. So we will see how to do that. Okay, so length of the tangent, if they say, it means that it's from a point on the circle where the tangent touches, that is the point of contact of the tangent, to the point from where the tangent is being drawn. Okay, somewhere outside. Understood? So this is the length of the tangent. Okay, now coming to the theorem. So the length of tangent, so now we know what the length of tangent is. So now they are saying the length of tangents drawn from an external point to a circle are equal. And we also learnt from this point, from the third point, that there are two circles drawn. two tangents drawn from a point outside a circle. And from here we learned the definition of what a length of a tangent is, right? Now here they are saying that if you have a circle and obviously a point P is there outside, so you can draw two tangents, right, from this particular point, then the length of the tangent, that is from here to here, is what is your length of the tangent. Okay, so the PQ is equals to PR. So this is what is the length of the tangent. See, if I extend this line, that is not meaning, this doesn't mean anything. Okay, you extend it how much ever you want, this doesn't make any sense. We are just bothered about the point from where it starts and where it touches the circle, this particular point. Understood? So these two, PQ to PR, is going to be equal to each other. Okay, PQ and PR. All right, so that is what we need to prove. To prove PQ is equals to PR, so first we'll write down the given thing. We just know that PQ and PR are tangents drawn from point P to circle O. Okay, so now we have to prove that PQ is equals to PR. Now we will do the construction. Okay, so the construction I have written in the blue pen, see, and I have made the construction also in blue pen. Join PO. So what are we doing? We are joining PO, we are joining OQ, and we are joining OR. Now what is this OQ and OR? Tell me. Can anybody guess what is OQ and OR? This is a radius, right? I hope you people have guessed the answer right. OQ and OR are the radii. See, the plural of radius is radii. Okay, so they are the radii of the circle. Okay, so now I'll come down. So we already learnt in the previous session that the radius and the tangent intersects each other perpendicularly, right? That's what we learnt in previous session. So now obviously we know that this OR and OP are radii, so this and this are going to be 90 degree, right? This is 90 degree, this is 90 degree, correct? They are going to intersect perpendicularly, so they both are equal to each other. So that's what I have written over here. Angle OQP is equals to angle ORP is equals to 90 degree. That is this angle which I have shown over here. Okay, ORP and OQP. OQP and ORP. These two are 90 degrees. Okay. Now these are angle between the radii and tangents. The reason I have written. So we learned this by theorem 1. Theorem 4.1. This is where from this we learned this, right? Okay. Now in right triangle OQP and ORP. So now we are taking these two triangles, okay? The right triangles OQP and ORP. So we know that OQP and ORP, we know that one of the angles is 90 degree, right? Angle R and angle Q are equal to 90 degree, and this PO is common to both the triangles, right? So if one of the side and if the angle is 90 degree and the radius is also equal to each other, right? So you have got the blue line common, OP common to each other, and OQ and OR equal to each other, and there is one 90 degree also. So from, in the last year we would have learned the RH theorem, right? Right, hypotenuse side and a right angle, right? The R over here stands for right angle. Okay, and H stands for hypotenuse, and S stands for one of the sides. Okay, so in this particular triangle, in these two right triangles, what do we get? We get OQ equals to OR. They are radii of the same circle. Okay, and OP equals to OP, which is common to each other. See, this is what I will just draw it over here, because it's difficult to scroll up and down. So see, this is P. This is how it is, right? This is O and this is P, and over here you have Q and R, right? This is Q and this is R. Now I am talking about these two triangles. See, OQP. So let me draw it with a different pen color. Let's say I use a blue color for this. Okay, OQP. Okay, and the next one I'll draw it with a orange color. Let's say you have got ORQ, correct? So I'm talking about these two triangles. Now in these two triangles, you know that these two angles are equal. this and this are equal. So this turns out to be one of the sides, right? This turns out to be one of the sides. And then you have this and this as 90 degree, right? So you got one of the sides, you got right angle, and then the third thing, OP and OP are equal to each other. For both of them, this is the same side. It's a common side, right? So I have written common side. So that is actually a hypotenuse. This turns out to be the hypotenuse for this right triangle. Correct? See, that's the side opposite right angle, right? So it's a hypotenuse. So by RHS theorem, we can say that triangle OQP and triangle ORP are congruent. So this is actually a symbol used for congruent. Congruent means equal to each other in size, shape and everything, okay? It's equal to the same, okay? So it's congruent to each other. All right. So if the triangles are congruent, then its corresponding parts, everything will be equal, okay? Everything will be, corresponding sides will be equal. So we have PQ is equals to PR, okay? So the reason is CPCT we write in short. This means corresponding parts of congruent triangles. Understood? So if two triangles are congruent, all their corresponding parts will be congruent. Congruent in the sense equal, okay? We don't use equal word for when it comes to geometry, when it comes to figures, okay? We use the word congruent, okay? So PQ is equals to PR. This is by CPCT. All right. So not only PQ, even all the angles, all the corresponding angles, everything is going to be same to each other, okay? So hence proved. That is what they have asked us to prove. So we have proved it. So from this particular proof, we have one more small little this thing. We can also say that, see, if you look at this triangle, you can say that this angle and this angle will also be equal to each other, again by CPCT, okay? So this means that, see, if you have an angle and if you have a line which divides this angle into two equal parts, that means this particular line is called as the angle bisector. Angle bisector, right? So that's because it bisects the angle into two equal halves, okay? Bisect means divides, okay? So this is an angle bisector. So here you see that's what I have written over here, a note. Angle OPQ is equals to angle OPR. So therefore OP is the angle bisector of QPR, okay? So that's one small note over there. So now we'll look at exercise 4.2. So this is numerical problems are really very easy. You can just use any of there are many ways you can solve this, prove this theorem, okay? You can solve using Pythagorean theorem also, okay? So now here we'll do one exercise 4.2. So here so the question, if you look at it, the question says that OP is given to you, QP is given to you, that is the length of the tangent is given to you. So let me write it down, okay? This is the length of the tangent, okay? The question says length of tangent is 24 and the distance from the point and to the circle is actually 25. So I have written those things in green pen and I have just given a name, okay? They haven't given any name to the circle or the point. So I have just given a name O and P over here and they are asking you to find the radius. So I just write this particular point as R, okay? This is what is not known to us. So I have put a question mark, okay? So now we will solve using a Pythagorean theorem. Because why Pythagorean theorem? Because this turns out to be a right triangle, isn't it? Because this is 90 degree. We know by theorem 1. The first theorem which we learnt in the previous session, this is a 90 degree. So this turns out to be a right triangle. So if you have a right triangle, you can actually use a Pythagorean theorem. So that's equals to Pythagorean theorem will be, see, this 25 is the longest side, isn't it? Because this is the side opposite 90 degree. Always the side opposite 90 degree will be your longest side, or this longest side is actually called as the hypotenuse. Okay. Yeah. So OP square, so the other two sides, OP square plus PQ square, these two sides squared and added together should give you the hypotenuse square, that is OQ square. This is what is your Pythagorean theorem. So your OP is actually R, so R square plus your PQ is 24, so 24 square is equals to OQ is 25, so 25 square, okay? So now we solve this. R square is equals to 25 square, we keep it as it is, 24 square, when it comes to the other side, it becomes minus 24 square, right? So 25 square is 625, 24 square is 576. You have done it over here, and then you subtract this, you get 49. So this is your r square. We need to find r over here, so we'll have to take the square root of 49, right? So square root of 49, whenever you take a square root of any number, you get plus or minus, okay? So square root of 49 is going to be plus or minus 7. But then, you know, radius, that is a length, can't be negative, right? So we just take r is equals to 7 centimeter, okay? We neglect the negative 7, that is minus 7, okay? So option A is the right answer. That's a multiple choice question, your question number 1. So that's A is the right option, okay? So now solve the remaining in your classwork. Again, in this page also, whatever notes I have given from the beginning, you have to write these things, write these definitions and the theorem and everything, and then you start with your exercise 4.2. Okay, so that's all. Your chapter circles is over. So you just have these 2 theorems. Please practice and you know, get thorough with it. It will be both the theorems will come for 3 marks. Okay. And also the details, the notes and the other points, whatever I have given, you have to understand it, okay? Because the questions could be framed in any ways. You should understand the question, understand the points. Only then you'll be able to answer. If you mug it, it's not going to help you, okay? So understand the points. All right. So complete the homework. So see you in the next session with a different new chapter. Allah Hafiz. Thank you.